All right, everyone, welcome back to the lab sessions for this deep learning course. And let's continue with our lab sessions. And today we're going to be conducting lab session number 6. Before I do that, let me actually share the link to this notebook. And I'll keep this over here. And you guys can open up your Google Colab notebooks where we can start coding right away. And so in this lab session, we're going to be starting with a completely a sort of a new domain in deep learning, which is called natural language processing. Till now, we've looked at computer vision, and then because that is something related to vision, now let's actually look at something related to languages, speech, audio, text processing, so on and so forth. And so the basic idea of natural language processing is to make deep neural net or like to make machine learning models understand language in general, right? Now, for us humans, it's actually quite simple. Like we probably appreciate it much, but that being said, it's actually not as easy for computers, for machines, because they have to understand a lot of things before they can even do simple tasks. Like I can give you two sentences and ask you to classify them. I can give you a negative comment and a positive comment, and you can probably very easily tell which is positive, which is negative. But before that, there is 20 years of like understanding of language that you have acquired, which has led to this position here where you can easily classify between two sentences. That includes understanding grammar, semantics, where do you put commas, punctuations, that is. Very subtle things like what pronouns refer to which, because they correspond to common logic. Like, for example, the cat didn't cross the road because it was too tired, right? Now, when I say this sentence, the cat didn't cross the road because it was too tired, what does it refer to, right? Now, we probably know that it definitely refers to a cat. It cannot refer to the road because roads cannot get tired. And so things like these common logic and all have to be understood by machine learning models as well. And so this entire thing is itself a very huge domain, and it's called natural language processing in total. Anyways, before we do that, let's actually start by just before that. Oh, actually, let me go back to the last lab session where we left. Give me a second. Right. Where we actually left last time. So the notebook is now available on the website, course website, and you'd see that now you don't have to sort of upload the data set on Google Colab. It's on Google Drive. It's directly downloadable via cloud. So make sure you look at that. And we did that, as well as created a final training loop. So we created a model, and then finally all we had to do was sort of pass it through a basic training loop that we've always created till now, right? Now I did one small thing that I put on the GPU, right? You'll see this is the code over here. And so the GPU part is actually very simple. X and Y converted to x.CUDA and y.CUDA, right? And self.model goes to self.model dot to and device within itself. Device would be, let's actually search for device. Device is equal to torch.device CUDA 0 if torch.CUDA is available, else CPU. So if torch.CUDA is available, which means GPU is available, this is named as the device. Dot zero basically means the very first core of the GPU. Like it's there may be multiple cores, but it has like the model we've built as of now can only fit in one of those. So CUDA 0 it is. And so when you run it, you'll see that the model would run very well. I don't. Okay, maybe I can run it and show it to you. It's not a big deal. And so you see that I can run it all over again, and can see that it sort of runs. All right, now it's actually it's showing that it'll take about 5 minutes, so we'll let it run till then, maybe. All right, which is actually quite good because, well, uh, otherwise, let's say if you switched off your GPU, would see that it takes a lot longer, something like a few hours at least, I'd say, just for one training cycle. Anyways, we'll see how it works. Let it run for some time. And till the meantime, let's actually continue our discussion on natural language processing. I think it's also a very good time, since now we define everything from scratch, and like all the code that we've written till now, our training loops, our metrics, everything we've written from scratch. Now, actually, let's sort of stop doing that, because it's you can't write everything from scratch again and again. There are wonderful libraries out there that do that for us. So we're gonna start looking into APIs as well. So at this point, I want to introduce you to a wonderful library uh, that has, in my opinion, revolutionized like this entire deep learning training, and it's made it very easy for beginners and advanced practitioners alike. And so that library is called fast.ai, right? And you can go to fast.ai, and you'll see that this is the website for it. The documentation for the library itself is given at docs.fast.ai, which gives you everything like what exactly do you do. And so Google Colab already gives us fast.ai as such, but it's sort of an older version. So what I usually do is I usually sort of install the updated version for it. And to do that, you do pip install dash capital U small q and again small q fast AI, right? And we'll actually push it through a temporary file, because so this is basically like whatever is the output of this. It's usually a very, so let me show you what I mean. When I do this, it's gonna give me a lot of output, like it's gonna show me the entire process that the Linux server is going through. I don't want to see that, so I usually pass it through a very basic file, temporary file, which I'm never gonna look at. So I usually, so this is the Linux command to push it inside something, and you put it inside a sort of a directory or a file over here. And so when I do this, it's called a TMP file. It's gonna not show anything. So that's good. So next, what I'm going to do is that, so everything, so if you go over here to fast.ai's documentation and you go to text, which is the NLP part of it. Right. Let's go to core. So the very first thing that you'd see you need to do is, okay, let's go to tutorials, beginner, text tutorial. And so you see the very first thing is from text.all import star, right? And so this would probably like import all the necessary stuff that we need. All right. Very first thing that I want to do at this point is download some data before we actually start with anything, because I think, and then we can probably define our problem slowly and better. So what I'm going to do is I'm going to download the dataset. And now FastAI actually gives me a lot of what do you call? It gives me access to a lot of data sets, including image nets and COCO data, like vision data sets, text data sets. A lot of those would be probably present over fast.ai/data sets. I'm not wrong. Um, course fast.ai/datasets, I think. Yeah. So these are data sets that you can find usually, like there are a lot of data sets you'd see over here. NLP data sets and image localization data sets, the variations of the COCO data set itself is a huge one. Image classifications, you'll see ImageNet, a smaller version of that, the Cipher dataset, MNIST dataset, and whatnot. That is actually given in this submodules known as URLs, right? And so let's actually take a look at what exactly datasets do we have. So these are all the datasets that you can find over here. You'll see. So what I actually am trying to look for is something known as the human numbers. This over here. All right. So I'll put it inside a URL name as this. And then FastAI also gives me a very convenient function that sort of downloads a data set, unpacks it, like unzips it or whatever, just unpacks the data and returns to me the path where all that unzipped data is stored. So let's actually, so that's given an untar data and followed by the URL itself. And let's actually look what the path will look like. All right, so the path is given in root slash dot fastai slash data slash human numbers. Let's actually take a look at what data do we have over here. So and again, FastAI is actually a very expansive library. It's a very wonderful example of good software engineering that you can do. So what they've done over here is that they've appended method to the path object itself, which you can directly use to sort of enumerate whatever objects are there, and that's given in ls. Otherwise, you usually have to do something like this, which would work too, I guess. You have to tap into, sorry. But then you have to tap into the Linux subsystem, which is actually not quite convenient. So they actually appended a version of that, which is basically a sub-object, a sub-attribute, which is ls. Quite convenient. So you see over here that you have train.txt, you have valid.txt over here. And let's actually take them all into one particular string, and let's actually see what that string is going to look like. So I'm going to do lines is equal to, let's create a list, basically, right? Right. And so so FastAI actually gives me a modified version of a list, which is given by this capital L. All right. Which is basically just a list, but it has a good number of functionalities appended to it. Let's not think about it for that moment, but I'll just go with simple reading of these documents given by this syntax over here. It's very common with open path slash train.txt, right? Path slash train.txt. As lines plus, which is basically append to the list itself, is equal to L star f dot read lines. So f dot read lines is gonna iterate through all the lines inside this train.txt. It's gonna put them in a list. This would by default return a list itself. Sorry, it would return a tuple of arguments, and then I'm basically converting this into a list. I'm adding this entire list into this master list over here. I'm going to do the same thing for my text document. I could have kept them separate, but I think it's. But we'll talk about why we are actually combining this into one large list. So let's actually take a look at why what happens slowly. So I'm gonna print this text over here, and you see this lines contains 9,998 items. Each line is actually one string over here, which is basically consecutive numbers returned sequentially in text, and that is basically this human numbers data set. which is 1, and this forward slash n is basically enter, or basically go to a new line. So we're gonna remove that. We don't actually need that. 2, 3, 4, 5, 6, 7, 8, 9, 10, and then I'd probably go. Let's actually print the first 100. So for ln lines 100, print l. So you see it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 20. So 11, 20, 21, 22, 40, 41, 42, 51, 52, blah, 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 all up to, I think it would be 99. Up to 100. All right. So it starts with 1, so it'll end at 100. All right. So that's the human numbers data set. So why I'm actually creating this data set is actually to create a dummy text over which we're gonna sort of do all the build our models. We're gonna define a problem. So we don't have a problem as of yet. We just have text. We're gonna define a problem and we're gonna solve it using deep learning. All right. All right. All right. So what I'm gonna probably do is this slash n is sort of unsettling for me, but I'll probably go ahead and remove this. And then we'll add in sort of, let's say, another identifier in between of them. I'm thinking of like a full stop, maybe like something like I would want my data set to be 1 dot 2 dot 3 dot 4 dot 5 dot and so on and so forth. The reason I'm doing this is because first of all, this slash n is sort of weird for me. So I mean, as if it doesn't matter, slash n can stay as is. And the reason I didn't actually, I'm just simply not converting this into 1, 2, 3, 4 is because for now I actually want to go sequential. So we're gonna slowly increase the complexity. Let's actually just take the data as is and sort of work on this. So the text that we're dealing with is basically, so I'm basically gonna do this, which is space dot join. Then over here I'm gonna start a list l dot right for ln lines, right? For line and lines. Let's actually look at the first 100 words. Like, what exactly are we dealing with over here? So now we have 1, 2, 1.2.3.4.5.6. By the way, strip would basically remove all these slash n's. It would even remove these spaces, anything that is not normal text that we want, and it would return us simply these other words over here sequentially. And so I'm sort of adding a space and a dot and a space in between any two words. That is basically that. All right. Let's talk about important concepts over here. So all these words are independent ideas, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 words, and they have 10 different meanings as such, right? So does 11, 12, 13, 14, 19, and 20. And now look at 21. It consists of two ideas. I can either go about it two ways. I can, number one, consider it as a whole. So 21 itself is a word. And so in that case, if you look at this data set itself, it has 10,000 words. And so 10,000 words has 10,000 independent ideas, right? And then I'm putting a full stop as well. And that's another new idea. And so I have 10,001 sort of concepts that I want my neural network to understand. Or I can sort of simplify it and say that, well, 21 is composed of two concepts, which is 20 and 1. So that's 20 plus 1. And I can expect neural network to sort of understand that understand these concepts. And in that case, you would see that the number of concepts we have essentially reduces to a lot less numbers. It would be in 30s probably, about, if I'm not wrong. And so and let's actually look at like how humans understand this as well. So humans ourselves, we don't consider 21 as a separate idea. We break it down as 20. And so I think it's only fair that we sort of break it down into uh, the required number of concepts. So these small concepts that we talk about are known as tokens. All right, and so known as tokens, and tokens basically are the smallest unit that you want your neural network to break it down into. You can break it down into as small as you want, but I think at a word level this is pretty fine. Like 1, 2, and 3 can be considered as 3 different concepts. Now if you want, you can go up crazy and you can do like, I can break down 1 into 3 characters, and O, N, and E will be 3 different concepts, but it just doesn't make sense to me, at least for now. So what I'm going to do is I'm going to break it down into tokens over here, and it's simply going to be text.speed, which is, I'm going to break it down into sort of break it down by space characters, like each word. Let's actually take a look at tokens. Right, and so it's, this is actually a lot. So by the way, a normal list would probably like list everything over here, but a modified FastAI version of this would probably give you a very compact representation of this. And if you guys remember, the reason this is actually possible is because of Dunder Repr, because Dunder Repr is basically what gets printed when you actually try to look up something. And so they've actually made it so simple that you can be, it will basically show you the first 10 characters of it, followed by dot 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 if there are more characters, and basically the length of the line. So it's a very compact version of it. Now if I actually just type in L over here, which is basically, I'm initializing the modified list version of this tokens using this as the argument, you'll see that it's a representation. So there are in total 63,095 characters up till 9,998, which is basically the length of the data set, right? So you'll see that over here, there'll be a lot of repeated concepts, like 1 will occur at this point, and then in when 21 will have been written over here. So 20 and then 1 will be repeated again. Then 31, 1 will be repeated again. So will 2, 3, 4, 5, and so on and so forth. Right. That's about that. However, I actually don't want all of the, I only want like, so my, since these are repeated, I'm repeated ones. All right. So it's actually not that bad. It's actually not that hard. All you need to do is, and I'm going to name it vocabulary. Vocabulary is going to be my list of tokens. All right. Vocab is the list of all tokens, unique tokens, that is. Because I can, when I have the unique concepts, these unique tokens, I can construct any concept from them in the domain which you're talking about. So it's simply going to be L tokens dot unique. And so that's basically a Python sort of method to actually retrieve the unique elements, and its implementation is that simple. It first converts it into a set, then it converts it into a list, as simple as that. And so to do that, let's see what happened to our computer vision model as such. And you'll see that in the very first epoch, we've actually reached 48%. What was actually the problem that we were trying to solve? Oh, right, sort of a binary classification. And at this point, it's actually not learning quite a lot, so it's less than 50% as of now, but you'll sort of, and it's under trained as of now, but you'll sort of train it for 10 more models and it will run. The point is that within 5 minutes you can train this entire neural network in one epoch. Run it for about 20-25 minutes, you'll get something. All right, I'll leave it at this point. Leave. All right, and let's actually take a look at vocab now. And you'll see that vocab is now just 13 different elements. So it's actually quite interesting that you can construct 10,000 words, the first 10,000 words with only 30 tokens. And in fact, not even 30, just 29, because one is this full stop over here. So this full stop should not be counted as such. Give me a second. Right. And so these vocab is going to be my basis for creating all sorts of models. So that's the very first concept that you should know about in NLP, which is known as tokenization. And tokenization is basically breaking down your language into small components that you would expect a neural network to understand independently. One is a concept, two is a concept, and I would expect my neural network to understand that. Now, there are different methods of tokenization. This particular method of tokenization is known as word level tokenization. Word level tokenization, which is basically splitting down each word as a separate, like taking each word as a separate token or a concept. There is character level tokenization as well, which is basically what I talked about, like taking O, N, and E as three separate concepts. And in that case, you would have 26 or 27 different concepts, including the full stop. Character level tokenization. And so different tasks require different, different methods are suitable for different tasks. For example, if you were go to the Chinese language, for example, there is no concept of a word in Chinese language. Because it's a pictorial language, and they construct each word very basic characters and strokes. And so in that case, character level tokenization is a better choice rather than word level tokenization. And so it really depends on the problem, what level type of tokenization you're going to be using. But usually seen that in English language, the word level tokenization works well for major tasks, for normal tasks. Now, you need to understand that machine learning models, or like computer systems, cannot understand words. So they cannot understand 1, 2, and 3. So I'm going to have to index them, sort of assign them a number with which they're going to be identified. And I'm going to create a lookup table, which is going to be useful for us. For example, I'm going to ask my model to predict 2, which is in computer language going to be represented by, let's say, a number n, right? And so for me, I'm gonna ask my computer vision model to predict that number n, and I'm gonna create a lookup table which is gonna help me convert that n back to this word to TWO. So it's gonna help me in visualization as well. So I'm gonna name this word to IDX, which is basically word to index, and it's gonna be a hash map or a dictionary, right? Which is gonna be taking the word as key and the element in the index as the value for it. So it's going to help me. So I'm going to pass 1 through this word through index, is going to give me the corresponding numericalized value. So you'll see, and then I'm also going to be sort of creating like a list containing just what do you call the numericalized version of them corresponding to each one of these words and vocab, right? Not in the vocab, sorry, in the tokens over here, which is 63,000 words. So let's actually take a look like how that works. Let's take a look at what word to IDX looks like. Word to IDX is basically, it has assigned a 1 to dot, 8 to a 18, 28 to the word 100, 0 to the word 1, 24 to the word 60, 21 to the word 30. Where's 100? 28 to the word 100, and so on and so forth, right? And so now I'm not gonna pass tokens into my machine learning model. I'm gonna be passing the numericalized version of them, so which is gonna be simply nums is equal to word to IDX I for I tokens, right? Let's take a look at nums. Nums is gonna be the same length but in numericalized forms, and this is what's going to be accepted by the machine learning model, right? That's that. All right. Now here's what I'm going to do. Let's actually define a problem, because now we just basically have data, but we haven't defined a problem as of now. I'm going to be defining a problem. The problem that I'm going to do is, given a few words from this from the text, which is 1, 2, 3, 4, all up to 10,000. Predict the next word that would occur. Right? So basically, if I give 1 dot 2 dot, I would expect my neural network model to predict 3, right? That is what I'm trying to do. That is what I'm trying to define over here. Now, you should know that what I'm essentially going to be doing is I'm going to be creating a data set which basically contains these inputs and outputs, right? So 1 dot 2 dot will be my X, 3 will be my Y. And then maybe 2 dot 3 dot will be my input, and then 4 will be my output for that. And then you should realize that even though I'm going to be creating this on my own, this has not been provided to me from self, right? I've engineered this. And so this kind of method of engineering is known as self-supervised learning. Let's talk about like what exactly is self-supervised learning. Self-supervised learning, and this is just my definition. Basically, an unsupervised learning problem that has been engineered to be a supervised learning problem. Why exactly do I want? So okay, so let's actually break this down. Let's get the problem that we are facing over here. So now I have this huge text over here, which is just a long string of text, random text. It has no labels. So it's an unsupervised learning problem. Now I hope all of you know what is unsupervised learning problem. What is an unsupervised learning problem? So it does not have any labels as such, but I'm gonna have to engineer labels for it to convert it into a supervised learning problem. Now, why would I even start with an unsupervised learning problem in the first hand? Now, that's because a lot of times it does not make sense to label the data. Text NLP is one of those cases. Many NLP tasks for that matter. Is because, I mean, your task is to make machine learning models or your deep learning models understand the semantics of the language. which itself is considered within the text itself. Like you don't need any additional data to understand the semantics of the text. Like ideally, you can ask your machine learning model to go through all of Wikipedia, all of the English language literature that exists in this world, and it will understand how, and it should understand how it works. And now, why do you want to convert a supervised learning problem? It's because a lot of these techniques that exist to learn these problems utilize supervised learning problems. Let's take neural networks, for example, deep neural networks. Deep neural networks essentially fundamentally work on the supervised learning principles. You need an X and you need a Y to sort of train a neural network. And so I'm going to have to convert this unsupervised learning problem into the supervised learning problem. And this process, this engineering process is known as self-supervised learning. It's at its core an unsupervised learning problem that has been engineered to be a supervised learning problem. So let's actually go ahead and start with what exactly I'm trying to do. So I'm going to create some sequences, right? I'm naming them SEQS, which is basically going to be, and I'm going to be creating, what do you call, 10, I'm going to be creating tuples containing X's and Y's, which is going to act as my data set. But my data set, again, is going to be 1, 2, 3, and 4. I'm going to have to convert them into numbers. And the numbers I'm going to convert into tensors because my PyTorch model is going to take tensors itself. So I'm going to write tensor nums I to I plus 3, which is I'm going to, so what I'm doing at this point is I'm creating a custom where 1.2 will give me 2 dot 2 dot will give me 3, 2 dot 3 will again give me dot, right, and so on and so forth. So I'm creating a data set like this, a sequential data set as such. And I'm going to be taking 3 tokens as of now, and we'll change it. We'll explore this later on, but it seems like a good starting point. And nums I plus 3, which is going to be my token, right? For I in range 0, comma, for I in range 0, comma, len tokens minus 4, because I'm going to have to stop early because of this thing over here, right? And I'm going to be skipping in parts of 3s, right? So I'm going to be skipping 3 chunks words at a time because third words. Right. So let's actually look at like what SEQX will look like. Token fine. Tokens for invalid syntax, right? Not a sequence. Torch nums I to I plus 3. Oh, sorry. Right. So I'm creating a tuple in which my input is going to be a tensor consisting of 3 values, 0, 1, 2, and the output is going to be a single number. I can convert it to a tensor. I'll convert it later on. But let's actually look at what 0, 1, 2 represents. So if you guys remember, 0 was 1. 1 is a dot, and 2 would be a 2. So basically now I have 1, 2, which is 1 dot 2 dot, and the output would be dot. Then I have 1 dot 3. 3 is three itself. So 2 dot 3 is the input. Sorry, 1 is dot, right? So dot 3 dot, and the output is 4, right? That's basically my input. right? And so this is basically a data set containing 20,000 data points as well. That makes sense because I'm sort of sort of dividing. I'm sort of skipping 3 elements at once in the 63,000 data set, so it's going to be returning 21,000 data points. That's fine. And so now I'm sort of creating my data sets and my data loaders. So of course I need my training and my testing data set, my training and my valid data set. So I'm going to, what I'm going to do is I'm going to sort of define a place where I want to cut my elements. So I'm going to do an 80-20 split. So it's going to be simply int len seqx times 0.8, right? Which is going to be the index of the element where index of the row, index of the word which marks the 80% length of this entire text. So now what I'm going to do is I'm going to do dls is equal to data loaders. Actually a fast AI method, not data loader, data loaders, right? Which is basically a fast AI method to sort of, it takes in data sets. It can take 2 data loaders and construct a sort of list of data loaders. And so data loaders is actually like this class in fast AI, which can sort of, like bring the training data loader and the valid data loader all into one place. So it's easy for me. And to construct it, it has various methods. Like for example, I can directly pass in data sets, right? So, so for example, this is going to be my training data set. This is going to be my valid data set, right? It's going to take in my batch size. By default, I'm going to put it 64 for now. And then shuffle, always make sure for NLP task is always false. Right? Make sure that shuffle is always false for NLP tasks. Why? It's very simple. It's very obvious because this text over here has only meaning because it's sequential in a way. 1, 2, 3, and 4 have to occur sequentially. Now, if I were to shuffle this, it would give me 1, 18, 2, 35, and so on and so forth, which is not the right way to go about it, right? Now, this might look like an easy example, but like consider like this English language that I'm talking over here. And if I were to shuffle the words randomly, it would not make sense. And I won't make my machine learning model learn anything, right? Because it's the sequentiality of words that makes sense. Right? And so, by the way this data loaders works is that train DL, valid DL is equal to DLs, and then I can simply go x comma y is equal to next iter train DL. Let's look at train DL, right? And then x and y, we can probably print them. Sorry. X dot shape, y dot shape, and they're going to be 64,3 and 64, which makes sense because we 64 elements in a batch, 3 items in one tensor, and that's it. Right? And now let's actually build our models. Building our model. And so over here, we are actually going to build the very basic model block of natural language processing, which is known as recurrent neural network. So I'm going to be creating recurrent neural networks, right? And let's actually talk about like what exactly is a recurrent neural network. Let's actually look at something. Right. A recurrent neural network is basically, can I enlarge this? Right. Right. A recurrent neural network is basically, it takes in an input X and it gives an output O, right? And now that is basically every machine learning model. What changes is basically the mechanism of what goes in this middle part, this model part, function part. A recurrent neural network is basically a small set of computations H, like maybe a linear layer H, right? But it does not take in all the elements of the X together. Like for example, if my X was 1, 2, it will not take them parallelly like a multi-layer perceptron neural network, or it will not slide through the each one of them separately. What it will do is it will actually take them sequentially. It will first take in 0 as the input. Whatever output go is taken by this edge again goes back into this as the input to this layer again. But on top of that, also be adding the second element. So there's I took in 0. I passed in 0 through this H layer over here. It gave me an output V, which I again took back to H, but whatever was the output, I added 1 to it. And then I again passed it through a neural network model. And I again passed it back into the same loop. And then I again added 2 to whatever was the output. And whatever was, now that my input is finished, that is my final output. And it's basically, and I would hope that my neural network would give me a 3 at this point. Whatever was the output that was expected. Now, why does it work? Is because you're sort of preserving the sequentiality of the model, which basically means that when you actually pass something as the input and then you again bring it back, you're sort of preserving the previous you're preserving the previous states of the data basically, and then you're modifying it slowly sequentially. And so this method is going to give you is going to preserve the sequentiality, is going to learn the sequentiality of the input itself, which is text, which is basically what we want. Now, we have looked at convolution neural network models, which preserve the spatial relations between pixels. The same way, recurrent neural networks preserve the sequentiality of the inputs. All right. So that is basically my recurrent neural network. If you guys have any questions regarding this, please ask at this point. All right. So I'm going to be creating my class RNN. It's going to always import from nn.module. Now the reason I didn't need to like sort of import this all because I imported FastAI's library and it sort of imports everything for me with it because FastAI itself is built on top of PyTorch. So while importing FastAI, you'll inevitably be importing your PyTorch libraries. There's always def in it, right? There's self, there's vocab size, basically like which will basically act as like how you're going to look up, how you're going to convert the number into whatever word that you sort of care about, right? I mean, I don't care about these numbers over here. I care about the words that they correspond to. So the vocab size. And the layer size of this hidden layer over here, which is known as H. Over here, it's going to be simply a linear layer. As you'll see, it's not as difficult. So I'm going to do, first of all, super dot init, right? But input H is going to be nn dot embedding. Okay, so what exactly do we first do over here? What will be an x? Now, x can be a single number, right? It can be a single number, or it can be, okay, it can be a single number, but the problem with single numbers is that it does not contain enough information to sort of give you meaningful values. That's the problem. You need slightly bigger tensors or vectors to sort of give us the input. And so in deep learning, there's a very common technique to sort of map lower dimension data into higher dimension data, and it's purely learnable, which is known as embedding layers. And embedding layers is nothing but 2D layers, are basically 2D matrices which act as lookup tables. So for example, I'm going to show you what NN.embedding is going to look like. But for now, just copy me what I'm trying to do over here. Now, let's actually look at what NN.embedding actually looks like. NN.embedding. It's simply a lookup table that stores embeddings of a fixed dictionary and size. Now, what does that mean? Here's what I mean over here. Let's say I have 30 individual tokens, and so my vocab size is going to be 30. And hidden thing, right? So let's say vocab size is 30, and hidden is 100, let's say 100. So let me do m.shape. It does not have a shape anyways. So let's actually look at what exactly emb is. Embedding. Now, embedding dot, look at is there a way to visualize the values of embeddings? There must be. Anyway, let me actually just show you what exactly is. So this will basically be a 2D matrix. 2D matrix of shape 30, 100. Now, what exactly is the significance of this is because it basically means that corresponding to each token, there is a tensor of length 100, which contains certain values. And these values are basically learnable, right? And so what I'm going to be passing 1 as my input. I'm not going to be passing, or when I'm going to be passing 0 as my input, I'm not going to be passing the number 0. I'm going to be passing the tensor corresponding to 0, which is simply given to me by emb0, right? Or tensor. Anyways, I'll tensor. And so it's going to give me 100 values over here. And now these 100 values contain enough information to be passed into the further layers of the neural network model. It's going to learn pretty well. And that is actually the magic of an embedding layer, right? It's going to be embedded layer of vocab size as the input and hidden as the input. So which means when input number passed through IH is going to give me a tensor of length and hidden, which will act, and then self dot hidden layer over here is given as NN dot linear and hidden as the input, because and hidden is going to be the output of this, followed by vocab size as the output again, because
Bhaiya,
yeah,
these 30 by 100 elements, these are all weights. Or are we converting 0 to that 30 by 100, which is going to be put in the network?
yeah, you can consider them as weights, or you can consider them as not weights, just values in themselves. So basically they're going to be acting as proxies to the number itself. So what I mean by that is I can, so over here what I'm trying to do is I'm going to be passing 0 as the input to this model over here, to this h over here at once, which is going to come back, and I'm going to be adding 1 to it, and then I'm going to be adding 2 to this, right?
Oh,
Do you
yes,
understand
yes.
that? Yeah. But then the problem is that 1 is a single number and it does not contain enough information for me to actually, for my model to understand, because one number will have then just one weight and one bias. And so it's not one weight and one bias is not going to have enough information for me to, like, for my model to understand the language. And so I need to sort of expand this into, I need to expand this into a bigger tensor, which will actually contain information, enough information from a model to learn. For that, I'm gonna be creating this embedding layer, and this embedding layer is not the same as weights and biases. So one way I could have done that is basically I could have passed it through a weights and bias layer, right? And the weights and bias layer would sort of learn something that would map any input to a certain output. So there would be, for example, the input would be 1, 100, which would, and then I could pass it into it, 1 into it, or 2 into it, and would 100 length vector, right? This is sort of different in the sense it's going to create a sort of weight and bias for each of those tokens separately, and each of those separate biases are going to be learnable. So you can consider it in that way. A better way to, but the problem is, and the thing is that what I'm trying to do over here is I'm sort of bypassing this weights and bias itself, and I'm simply creating a lookup table, which is a matrix of shape 30, 100, in which all of those values itself are learnable. Like they have gradients activated in them. And so it's basically the same as initializing 30 weights and biases, each of them which would give me 100 length vectors, so to say. I'll ask you to read this up, this documentation over here, and probably what is an embedding layer network. We can probably look it up and you'll find some really good over here. But do you not understand anything now? So, okay, even they do not visualize it well, but images probably. Right. This is a good example. I'll open this in a new tab. And so here's what I'm trying to do over here. Forget about all these orange, two different things over here. This is basically a 2D matrix that you see over here. And the input to them is going to be, and so when I'm initializing a matrix of 30, 100, I'm basically saying that initialize a tensor of length 100 corresponding to each of those 30 vectors, each of those 30 tokens that I'm talking about, right? Yes or no?
Yeah,
You
yeah,
understand
yeah.
that?
थोड़ा
If you don't understand it, I'll explain it again. It's a very important concept in NLP in general. So here's what I'm trying to do. I'm gonna be I have 30 tokens in general, which is basically my entire language model for now. Like I can this is my small problem, and in this small world, these 30 tokens is basically defining the entire language. I can extend it how much ever I want, but for now, let's actually stick to a problem. There are 30 tokens in total. 30, right?
Yes,
In this recurrent neural network model, I'm going to be passing one token at once
right.
into this hidden layer, which is going to be a linear layer model, which basically means that there's going to be one weight and one bias, which I'm hypothesizing is not going to be enough for my model to understand the label itself. So what's one way you can do that? You can probably extend this to a bigger tensor,
Okay.
right? And that is over here. Each word, each number 0, 1, 2 up till 30 is gonna have its own 100 length tensor over here. And so now I can consider this 100 length tensor as a representation one single word over here, over there.
Okay. And that conversion is learnable. So
Sorry?
that conversion that we're doing from 0 to the tensor, which has more information, is
Sharia, your voice is
learnable.
breaking. Yeah, this is totally learnable, and the purpose, and basically you can train it end-to-end gradient based, which basically means that the deep learning model will assign values to this tensor in such a way that maximizes the information retrieval process. Basically, that is the point.
Yeah, I understand. Thank you.
Understood? And so this is not the same as passing this 30 vectors or the one vector at a time into sort of a 100 layer through a weight which will convert it into a 100 length vector. The reason is because in that case you would be assigning one weight and one bias to all of those 30 vectors, all 30 tokens, which basically now they're sort of dependent on, which is not the case, because they're all independent concepts. So you would want different weights for each one of them. So consider this 100 length bias as, like there was token, and then there was one weight corresponding to that one token, and it gave me 100 length vector. And each of those 30 tokens had separate weights and biases. You can look at it in that way. Or I simply simplified it in a way that I basically created this embedding layer, and that embedding layer is basically that. Creating separate weights and biases for each token for it to have a for each token to have a better representation, a tensor which can potentially contain more information than the one single token itself. Do you get the idea?
Yes, I understand. Thank you.
Okay. But good point, good question actually. So I'll at the end of this lab session, I'm going to be posting some reading material for this embedding. It's a very important concept, right? And so, anyways, let's actually continue. So the input was vocab size. The output also has to be vocab size. And now this is simply going to be something similar to a classification problem, in the sense that whichever layer, whichever like row or whichever element in the vocab size tensor is going to have the maximum value, I'm going to say that corresponding token is basically the prediction of the model, and I'm going to look it up in my dictionary over here and say that the model is actually predicting that word. Doesn't sound that difficult actually, but not that. Actually, I'm going to be expanding this into another, sorry, my mistake. Anyways, I mean, you see over here that the hidden layer takes an input and gives an output, and that output again goes as the input. So the hidden layer obviously has to be like the input and the output have to be of the same shape, of course, right? My final output, however, is going to be that what I was talking about, which is basically nn dot linear and hidden, comma n, sorry, vocab size, right? Which basically means that I'm at this point I'm going to be sort of taking the output, passing it through, and getting a vector of length, tensor of length, vocab size, and then whichever element has the highest activation value within this, I'm going to be looking up the table and say that the model is predicting this word to be the next word, right? As simple as that. So finally, it becomes a classification problem as such, right? It's a classification problem, right? Because the model has to choose among 30 different values. So I'm going to be writing over here that this essentially is a classification problem. Right. Finally, I have def forward, right? Forward self x, right? And I'm going to be initializing this variable known as h is 0 initially, right? And what I'm going to do for I in range 3, right? Because there are 3 elements in this word over here, and I don't want to hard code this as of now, but it's just a dummy model, so I'm going to hard code it as of now. Later on, we're going to be creating methods to sort of automate this as such. So h is equal to h plus self dot ih x I. So everything comma I, which means first taking the 0th index, take it, pass it through this hidden layer, and then h will become basically that. Once you're done with that, this basically, after each linear layer combination, you always know that there is always a ReLU, right? So we pass it through we're gonna pass it through ReLU, right? F dot ReLU, right? Self dot h comma h h. What I'm doing is first I'm passing it through the embedding layer, and then finally I'm passing it through the linear layer, this layer in the middle, this one, and then each one of that I'm going to be passing through a ReLU. Again goes through that. Again goes through a ReLU. Again goes through it. Again goes through a ReLU. Finally, the output is given, and finally my output will be return self dot h o h. Okay. Let's actually look at what this is going to be look like. How this is going to run. Let's actually look at. We already looked at like what our x's and y will be. So model will be RNN. Vocab size will be len vocab, right? And me embedding size, I'd say let's take 64 or maybe even 100, doesn't matter, right? So let's actually look at model x dot shape, if this works. X and y are defined. So let's actually pass an x. Let's type x dot shape as well and x dot shape. You're gonna is x 64 comma 3 and the output is 64 comma 30. That's a mistake, I think. Oh no, 30 is correct because output should be vocab size. And then let's actually look at model torch.arg max model x. What does this mean? Dim is equal to 1. Right. So basically, this is basically telling me the indices. So there are 64 elements in a batch. Each 64 elements has 30 output vectors corresponding to them because it was passed through a linear layer. And then because it's a classification problem, if you remember, what we essentially do is we check which index contains the maximum activation value, which is given by this torch.argmax. And that I'm going to be passing through basically this. I'm going to be looking up basically. So I'm going to need actually another list over here, which is basically the inverse of this to look it up. So so IDX to word, I'm going to name it IDX to word. IDX to word is equal to word, index word for I comma W, which is basically the opposite. So this was word index, this was index word for IW and enumerate. Oh, in for okay, no, let's actually do something like this. Word to index I for I in word to IDX. And so let's look at IDX to word as well. So what I'm going to do is now basically let's for I in or index in torch.argmax. Okay, so res is equal to, I'm gonna create an empty list over here. So res dot append idx to word idx. Let's actually see if that works. And so forth. You can't pass it index, so I'm gonna be checking because the this index over here is expecting a number and not a tensor. So PyTorch get value from tensor. Dot res. Right. Over here is going to be basically the output of these 64 elements over here, and the model is basically predicting that as the next output. Right now it has not learned anything, which is why it's all random, but you see that this model works this way. All right. How to evaluate. Anyways, this is done. Let's actually learn, like I put this model to learn. So if you guys remember that we actually created a class called as learner or a trainer or whatever, which basically contained my optimizer, my model, my DLs. It defined a training loop. FastChat does the same thing for us. And basically it's given in the learner class. So it takes in the DLs, it's going to take the model, it's going to take the loss function, which is going to be f dot cross entropy, because it's essentially a classification problem of 30 differences, right? And metrics, which is basically what metrics do you want to evaluate it by, is equal to accuracy. I'm going to name it accuracy, right? And I'm going to do learn.fit 3, comma, and learning rate itself, with learning rate, I'm going to say something 1 in x3, which is 0.001, 0.001, right? Let's see how it works. As you see that right now it's giving me sort of very bad accuracies, right? But that's perfectly fine, because you'd see that okay, maybe let's even try to sort of run it for 30 epochs, maybe. Not 30 epochs, actually. 10 epochs is good. 30 epochs is too much. 10 epochs. 10 epochs is good enough. Let's actually see. So you see, I'm sort of going with 33, 30, 40% accuracy as such. 40% accuracy is the maximum accuracy I can get. Now you might say that this is a bad accuracy, but trust me, it's not that bad of an accuracy for two main reasons. Now, the number one reason is that if, let's say, if my model were to predict the model a completely random word, right? So the average accuracy that I would get in that case would be only about 0.03 accuracy. So my model is definitely learning some things, right? But the problem is that, and the second reason that this model, I'd say that is not working bad, is because because language tasks usually accuracy is not a good measure for the reason because when I say 1 2, forget about 1 2 3, but let's say like I like dogs and dash. Now I can fill in a cat, I can fill in a zebra, I can fill in pizza, I can fill in uh, this pen, for example, and all of them are semantically right. But for a model, accuracy and it's always right or wrong, right? My model will probably not give me a good result. It doesn't necessarily mean that it's not learning the semantics. Also, having said that, we'll actually take it to a quite a higher accuracy. But having said that, this model is a very simple. It's not simply enough to understand the model, the semantics of the language. And so that is basically the problem over here. Now, let's actually try to improve this model as of created a basic recurrent neural network model. Let's actually try to improve this model over here. So what I'm going to do before that is we're going to sort of find a problem that we've actually done over here. The problem basically is that each epoch and each element of the batch, right? Oh, forget about in each epoch, just resetting this h to 0, which basically means that nowhere that this model can go beyond 33 or like go beyond 40% accuracy, because each time you're passing it through the model, you're resetting it back to 0. So you're not sort of learning iteratively. So each epoch is basically the same. So if I write learn.fit 1 or a learn.fit 10, it's going to be the same because model is always doing a 0 at that point there. So even in the computational graph, that 0 is going to compute to no gradients after that. And so that is basically a problem that we are facing as of now. Now, is not wrong as such because you're basically initializing it to something and then you're adding values to it and so on and so forth. But we need a way to sort of preserve the state of the recurrent neural network models. Now we need to preserve state of the RNN or the progress of the RNN through epochs, through epochs. And the way to do that is to need to get rid of initializing h is equal to 0 during each forward pass. And the simple way to do that is to simply, we'll actually modify this over here. And the way we'll do that is we'll sort of, let me actually copy paste this. And what I'm going to do is that I'm going to, instead of putting this over here, what I'm going to do is I'm going to be sort of initializing the h as one single parameter, one single what do you call one single attribute of this class itself, which you can initialize it all at once at once. And now this h over here has to be converted to self.h, 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 self.h. Now ideally, I don't want my model to always be stuck at this. And so whenever I want to sort of give an option of sort of and the only thing that you need to do in order to sort of do a totally fresh computation on that, because here's the problem that you're going to be facing over here. After each pass, each epoch is basically okay. So my mistake, actually, I was talking about epochs, but not through epochs, but within the epochs also, you sort of divide it in different batches. And the problem with the neural network model is that in one epoch, across different batches, also the h was initialized to 0 again and again. Each epoch, however, now is computation. It does everything from scratch. So I want to give my class, recurrent neural network model class, to sort of have the ability to reset itself. So I'm just simply going to be writing self.h is equal to 0. So I'm basically giving my neural network model to what do you call, to sort of reset itself back to 0 whenever it wants to. Here's something else that I want to do over here. When I get self.h out from here, instead of doing this, what I need to do is sort of detach this self.h from a main computational graph. The reason I'm going to be doing that is because the state of the neural network model is basically contained within this part, right? And this is basically the h, which is going to contain all the information corresponding to your language itself. And just give me a second. And so what exactly happens is that this h is going to be responsible for learning the semantics of the language. And this needs to be learned effectively. It has to be learned well. The 10,000 elements. Okay, forget about, right now we're just dealing with 3 elements over here, right? And 3 elements over here. But let's say that there were 10 elements input, right? Which is actually it's actually very common now. So effectively, you're dealing with a 10,000 layer neural network, sort of, so to say. Like you're passing it through 10,000 linear, and your model to sort of propagate all the way back over there when it's calculating gradients. That is fine, but the problem is that when you're actually going to do it across all batches, all separate batches, it's going to become so large that self.h is going to be basically facing the problem of vanishing gradients or exploding gradients, which we basically talked about very briefly. That basically what happens when you pass it through a lot of neural network models. Let's say a linear layer shifts the mean standard deviation by just a factor of 1.1. Then you do it enough number of times and it will basically explode to such a large value that your GPU cannot understand that. And so the solution to that problem is to tell PyTorch that we do not want to backpropagate the gradients through the entire sort of 10,000 layer neural network model. Instead, we just keep the last 3 layers of this, right? And that is basically what we want, basically, because I mean, the output of this 64 1,3 input, the output of where is it, 0, 1, 2, this one over here is only affected by the 0, 1, 2 and not by this any other element inside other batches, and so to say, right? That is what defines the classification problem. And so I'm gonna have to sort of detach this from the computation graph. I understand it might be confusing, but I'll reiterate through it once. So I'm gonna say that out is equal to self.ho self.h, and I'm gonna say that self.h is equal to self.h.detach. I'm gonna simply doing return out at this point. Now, basically, what I'm doing over here is that, well, what I'm basically telling PyTorch is that initially I didn't have to do this self.detach because self.h is equal self.h was reset to 0 every time this was run for across different batches. And so the problem with that was basically I was losing the values of h itself. The values of h, now I don't want to lose the values of h because h contains the information about the neural network models itself, right? So across different epochs, finally, when I'm going to be finishing my epochs, I want my neural network model to understand the semantics of the language, and that h has to be learned iteratively, right? And across batches as well, right? So throughout the entire process of 10 epochs or 15 epochs, I would want my h to be continually improved, but I cannot afford to calculate my gradients all the way back only because each output is only determined by the last 3 inputs. And so the way to deal with that is to detach it from the computational graph that I did over here. And I've also given us an option to sort of reset it whenever we want to, right? So that is that. Okay. Let's take it one step further and let's actually talk about like what exactly else is the problem over here. The problem is that our model is not learning sequentially enough, in the sense that let's actually talk about this 64,3 input. So what do you expect the 64,3 inputs to be? The first element in the 64 element will be 0, 1, 2. The next will be 1, 3, 1. Next will be 4, 1, 5. Next will be 1, 6, 1. 7, 1. And the problem with batches is that batches don't. Oh, okay, let's actually talk about that for 1 second. But let's actually just run this model over here. And I have to sort of initialize my model again. Model is equal to RNN2. It's simply going to be the same as before, which is going to be Lookup 64. Okay. Let's actually run this. Let's see if we get any better accuracy. So see that there's some mistake. I'm not exactly sure. 47. That's h plus a h x comma I. Size of tensor as 64 must be the match of size tensor p 47 and non-single dimension. Well, that's weird. Wait on this again. That's weird. This is happening in the validation epoch. Non-singleton dimension. H dot H I self dot I H weird. And I can't understand where the problem is, but let's solve it. We'll probably solve it. Give me a second. Meanwhile, if you guys can figure out something, do tell me. Let's pass in sort of. Oh, I think I know the issue. Okay. Here was the problem that we were facing. The problem was that the last batches, the model actually divide. So the way we actually build a data set is that we divide a data set into batches. Batches 64 elements in one batch. But the problem is that there may be one case in towards the very end when there are just not enough elements to fill the entire batch. So the batch is essentially of a smaller size. Now, usually it's not an issue because each batch is considered independently and is passed through the model independently. The problem over here is that now you're actually trying to feed in, you're actually trying to add two batches separately, right? And so if they're going to be of a mismatch, there's going to be a mismatch in the size of the batch size itself. It's not going to work itself. So FastAI also provides me a method to sort of drop this last batch, which may contain a low number of size. So if the number of batches don't match, you can actually simply drop it. That's all. So that's that. So now the problem is solved as of now. And you'd see that the model is working. Okay, let's actually run it for a few more epochs. Right. Okay. So now I see that I have reached a 50% accuracy, but all right. So let's that's all right. I mean, you guys, the problem now is something else. So now I just wanted to show that this works. So now let's actually let's sort of find another problem that I can find over here. All right, and then what we'll do is that we'll sort of implement that, and let's see where exactly do we go from there. All right. Now here's the problem that I want you guys to see over here, which basically is that, well, uh, this sort of method that we looked at over here is actually, there's a specific name to this. It's actually called backpropagation through time, and you see this quite often in a lot of places. This particular type of backpropagation in which we sort of only propagate a few layers back in time and not through the entire sequence, but we still retain the entire sequence. So that's that. The problem with but the problem with this now is that you're sort of giving it random data altogether, right? Because batches, the elements of a batch are considered separately. So effectively, the model is looking at 1, 2, and then 3 as the output, and then the next output, which is actually coming from the next batch, and the same element over there, same order over there, is going to be 65, 66, 67, so to say. And so the model is actually, you're giving it completely a very skewed representation of the data itself. And so what I'm going to do is I'm going to sort of rearrange the data in such a way so that the batches contain not 1 and then 2 and then 3 separately, but 165, 120, something like that. 165, 128, 164, 128. And the second batch will contain 265, 129. Third batch will contain 3. So what exactly will happen when I'm passing different batches? The model is going to see 1, 2, and 3 sequentially. So that's what I'm going to do, right? And to do that, I'm going to be defining a few things. So I'm going to be defining a definition, a function known as def group chunks. It's simply going to be, which is going to take a data set. It's going to take the batch size as well, right? And what I'm going to do is m is equal to len ds divided by ds, which is going to be basically the elements in each elements in each elements that will contain each batch. The new data set, I'm going to be initialize this as a list first. Now what I'm going to do is for I in range m, new ds plus is equal to l ds I plus m star j, right? For j in range ds. Right. And I'm going to be simply returning the new ds, which is going to be a list of elements. That's all. Anywho, what this is gonna, so let's actually look at like what this is gonna return finally. So group chunks 6 yes, right? And then batch size is basically 64, let's say. So you have 0, 1, 2. The same batch contains 11, 1, 2 rather than 1, 3, 1. So ideally the element should be 0, 1, 2, 1, 3, 1. And then let's actually look at 0. So the 0th element. Oh, right. So anyways, I've sort of so redefined the elements, and now if I were to go to the 65th element, oh sorry, 65th element would be whatever 64th element. Sorry, that is 65th element, but it's indexed as 64, so it will be 131 now. And if I were to go 64 times 2, right, minus 1, it would be 4, right? And so what I've basically done is I've sort of rearranged this order in order so that when I'll actually be sort of running it through when I'm constructing batches out of this, it's gonna when I'm actually going to be constructing batches out of this, sequential batches are going to be like different batches are going to be sequential in order, and the model is going to learn better. So anyways, dls is equal to data loaders dot from the sets, right, group chunks. So this is going to be my modified data set, and it's going to contain sex cut. Batch size is going to be 64, right? I'm going to this is my validation data set over here, which is group chunks, sex cut. So batch size is gonna, oh no, wait, different order, sorry, should be separate like this, cut and cut over here as well, and batch size for again. Batch size is equal to 64, drop last is equal to true, right, and shuffle equals false. Always shuffle equals false. That's that. So now let's actually, so yeah, that should work. Now if I construct my learner this way, and now let's actually run our model. Let's actually see what happens. Better accuracy, you see, 47, 48%. Way better than the accuracy that we reached over here, and of course than the one we reached over here, 38%. So we've sort of improved the model, but now the only bottleneck remains is the complexity of the model itself. It's not enough. That's it, right? But that's that. Let's actually do a small tweak to this problem, which will actually help us improve the accuracy even better. But before that is we're actually going to be making this task slightly more challenging, not only for this but for the other tasks as well, right? So what I'm going to do is that I'm going to be sort of right. So what I'm going to do over here is that I'm going to be we're going to improving our accuracy. So for that, what I'm going to do is first I'm increasing the complexity, and what I'm basically going to be doing is that of increasing the complexity of the problem, right? And what basically we're going to do is that instead of just 3 tokens, we will use 16 tokens at once into the model, right? And predicting the next sequence of tokens, right? Next 16 tokens, so next sequence of the words of the words. This is variable, by the way, so the 16, so you are free to change the length of the sequence. The purpose of doing that is doing this is that we want to use PyTorch's internal RNN functions, which actually gives us much more flexibility and much more ability to increase the complexity. And let's actually look at why I'm actually doing this. So let's go to PyTorch RNN function. Thing is that RNNs sort of taken so it takes an give me a second. Torch.rnn. The thing is that PyTorch's RNN function sort of gives us the same output shape as the input shape, right? Which is why we were actually trying to use that. But anyways, we'll actually tap into that later on. But first, actually, let's forget that. Let's actually first contain build the data set itself. So the sequence length is going to be 16 as of now, and you can change it as you want. And the sequences now will be L tensor nums I through I plus SL, right? And the output is going to be tensor nums I plus 1 to SL plus 1, I plus SL plus 1. Right. So basically, okay, and then this would be for I in range 0 len nums minus SL minus 1, right? And then you want to skip by SL times at once. Right. Let's actually take a look at what these sequences will look like. Sequences look like 0, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6 as the input 1. And the output, there's a mistake over here. There's a mistake, I feel. Oh. Right. And the output is going to be just basically shifted by 1. So I'm going to be removing this and I'm going to be taking this, which is over here, followed by the next element. So I'm basically predicting. So my now task is to predict the next sequence of this rather than just one token itself. Reason is because I want to be using PyTorch's internal RNN function. Now, there's nothing special about the RNN function. It's basically just a modified version of what we are writing over here, but just to implement that complexity, increase that complexity, I'm not going to be writing it from scratch. I'm going to be using PyTorch's function. And PyTorch's function by default only, so it takes in a certain input and it gives you the output. Not this, but forgetting the name. NN.RNN. So not torch.rnn. I want to be looking at torch.nn.rnn. Yeah, which is this. Num layers bias dropout. And so you see that it does not specify out shape because the out size is going to be literally the same as the input shape or whatever is the vocabulary size basically. Anyways. Let's construct our data loaders, right? But group chunks, so cut is equal. So let's define my batch size as well. Batch size is going to be 64 as of now, right? And so what I'm going to do is that cut is equal to int len sequences times 0.8, 20 split, right? 80-20 split. Now next is going to be data loader. So data loader is simply going to be data loaders from dsets, right? And I'm going to be taking Basically the same thing over here, group chunks over here, right? Let's see if this is right. Group chunks, cut, batch size, batch size. I'm going to be renaming them as batch sizes and not hardcode them anymore. Right. Hope this works. Yeah. Okay. That's that. Int object is not callable. Oh, star 28. Right. Right. Okay. Let's actually create our modified RNN module over here, which is RNN3, I'd say, which is nn.module. Right. Same stuff as before. Let's basically copy this as of now, and then we'll modify it later on slowly. I'm going to be copying this over here. Right? And right. Basically, IH nn.embedding, HH nn.linear, HO nn.linear, and then self.h is equal to 0, which is a one-time initialization that we possibly have the output to sort of reset whenever we want. And now, since I'm not going to be predicting just one value, right? I'm going to be predicting 16 different values, right? So I need to run my hidden layer. I need to pass each input through the hidden layer separately. I need to sort of store them separately. The thing is, because I'm going to be passing in H, and H is capable of giving me just one output, which is basically a 30 length vector, which contains one maximum activation. Right? And so to construct 16 different tokens, I'm going to have to pass 16, like I'm going to have to pass it through this H hidden layer 16 different times. And all of them together, I'm going to concatenate them into one, and then I'm going to pass it, that is the output. And then what I'm going to do at the output layer is basically for each of those 16 layers, find out the maximum index, like the index which contains the maximum value. And for each of those 16 values, that will be the output, and that will be done for all the elements in the batch as well. Hope that makes sense. Either way, so what I'm actually going to have to do is let me actually just remove this forward function over here. I'm going to say outs is basically a list of 16. It's basically an empty list as of now. What I'm going to do is for I in range SL sequence length, self.h is equal to self.h plus self.h x this comma I. So this is the standard thing that we did over there. Self.h is equal to f.relu self.h hidden layer, and then followed by self.h. Finally, I'm gonna do outs.append self.ho self.h, basically the output of that. But I'm gonna have to do this for all the elements in the sequence length, right? Which is basically done by this I over here. So initially there were just 3 elements, now 16 elements. I have to iterate across all of them. Finally, of course, self.h is equal to self.h.detach. Right, that's that. And finally, I'm just going to do return torch.stack outs dim is equal to 1. Basically, stack across the last element, the last dimension. That is that. So the output shape is going to be something like batch size, sequence length, vocab size. So I need to stack across this layer over here. That's that. By the way, if you want to, let's actually look at like what exactly is my x and y going to look like. So train DL valid DL is equal to DL's and then x comma y is equal to next iter train dl, right? X dot shape, y dot shape. So as of now, the input is 64 comma 16. For each of the 16 elements, there's going to be there's going to be 30 length vector that's going to be put out. So now let's actually look at define a model. So model is equal to RNN 3, then vocab size, app size, and then output is going to be hidden. So what was that? 64 plus 6. What was this again? The value that we put 64, right? Just a parameter value, doesn't matter. So now let's actually do x dot shape. And then 3 is not defined. I didn't run this. Okay. Vocab size is not defined. Oh, vocab, len vocab. Okay. So you see the output is 64, 16, 30. All right, that's that. Now, before we actually move ahead, we're actually going to have to modify what do you call it, the loss function. Because the traditional loss function which is given by PyTorch and which we've been using is only, acquainted with two-dimensional values. So for example, batch size, comma, whatever values. Now we have three-dimension vectors, and the method of computation of the loss will be slightly different. So we'll have to sort of rearrange this because we stack the outputs unconditional. So that is basically going to be def loss func is equal to, and then input target. So what I'm going to do is return f dot cross entropy. Basically, what I'm going to do is that I'm going to sort of reshape this into this is going to be batch size, and this is going to be len vocab. Comma target dot view -1. Basically, what I'm doing is that target is just two-dimensional. So target is simply 64, 16. And so what I'm doing is I'm sort of flattening it out sort of into one long tensor. All right. Over here, what I'm doing is I'm preserving the batch size over here, and over here, len vocab. So by the way, you need to understand what's going to be the input to this. So the input is going to be let me actually. Okay, so this input is going to be initially input is going to be what batch size times SL, batch size times sequence length times vocab size, right? And target is going to be batch size, comma vocab size, sequence length, right? What I'm going to do is that let's actually consider these. We're basically converting this into the traditional two-dimensional thing, in which we're basically going to be flattening these two dimensions out. And so this is basically done by this -1 over here, right? It's as simple as that. That's that. So simple as that. I'm going to go for learn is equal to learn. Learn is equal to learner. DL's RNN 3 len vocab. So I'm initializing my model over here, comma 64, right? Loss function is equal to loss func, which I've defined over here, right? Metrics is equal to accuracy, right? And then I'm going to be passing in another argument over here, which is known as the model resetter. What exactly is this CB? CB is actually a callback, and callback is nothing but I will talk about what that is. Let's talk about what exactly model resetter is. So the model resetter is basically before the training procedure. I'm going to call in that before the validation procedure. I'm going to call in that. Okay. What exactly is a callback? So the CB stand for callbacks, right? I'm gonna run this as of now. CB is equal to callbacks, and I'm gonna stop as of now and we'll continue next time. But what exactly is a callback? A callback is nothing but a function that is called at a certain time, at a certain stage of the training procedure. So let's actually look at our older training loop. If you guys uh, remember, which basically we wrote a training loop for x comma y in DLs, passes through the models, uh, pass it through the models, and then do something, and then pass it through the loss function, do loss dot backward, do the gradient update, and so on and so forth. Each of these steps, if you guys remember, I always put comments saying that this is step 1, this is step 2, this is step 3, and this is step 4. And in between all of those steps, fast AI gives you an option to call certain callbacks, you know. And so let's actually look at the definition of the learner function over here. Learner dot, yeah. So there's learn.fit over here, and basically what I'm doing over here is do self.doFit with self.epoch is equal to with events do epoch. So DLs blah 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 all batches one batch self.iter is equal to I. Yeah, here's this. So it takes in an input, it passes it through the model, and it gets some prediction. Step 1. If you guys remember, we passed it through the loss function after that and got loss, and then when we did a backward, loss backward. Between each of these stages or steps, what FastAI has done is it's sort of introduced some sort of this function over here, which is actually a callback, which is basically calling all the callbacks which have this after pred defined, which is basically once I've completed this prediction, is there anything that you want me to do apart from this basic training loop? Once you've calculated the loss, is there anything that you want me to do this part after loss before? And then once I'm done with that, I'll go ahead and I'll sort of do backward. Before calculating gradients, do you want me to do anything? After calculating gradients, do you want me to do anything? Before calculating the optimizer, do you want me to do anything? Before, after doing the optimization step, do you want me to do anything? That is given by this things over here. So now let's actually go to the definition of this model resetter callback that I'm putting over here. And you'll see that basically what it does is that before the training starts, do a self.model.reset. All right, makes sense. Before the validation, because it's a completely fresh run, do again a model.reset. And once you're done fitting, do a model.reset so that you have the option to run that function again if you want to without, doing all that stuff. So that's that. This is that callback thing that I'm doing over here. Now I'm simply going to be doing learn.fit. I'm going to stop at this point after this. 15, maybe 15 epochs, and then three sounds like a good. And I'm going to train it for longer for 15 epochs because it's a sort of a more complex task, so it needs more time to get across this. And let's actually see what we're getting. So 45% accuracy, 46, 47, 48, 50, 51. All right, 51% accuracy, and I can actually run it for longer. I personally have come across, and let's do learn.fit one cycle actually. Okay, either ways. So we were able to reach a 50% accuracy, and I personally have reached even 70% accuracy using this, 65% accuracy to be honest. And I'm very sure I'll be able to reach it if I don't know okay, let me try one sec. Let me try modifying this slightly. 1 neck 4 maybe. 0.2, no, not working, not working. 1 neck 3 maybe. 20, 27, 40, 45. Okay. 3 neck 3. %47 accuracy. What if I increase it to 1 neck 2? Okay, anyways, I've reached this 50% accuracy mark, slightly even better than this mark over here. I personally have reached 65% accuracy. Next lab session will actually see how we'll continue from here, and we'll sort of increase the efficiency of this model even further. And then we'll also be looking at the transformer models. Also, after this, we're done with these basic RNN models. We're going to be looking at LSTMs. We're going to be looking at LSTM models. And then finally, we're going to also be learning how to implement transformer models, which is actually one of the most revolutionary things in the very recent years in deep learning. And we're going to train our models based on that. All right. So thank you guys, and see you guys next time.